Hello, welcome back to chemistry. This is podcast 10.3, where we're going to learn about heats of reactions. This is Miss Gray, and today I am joined by the lovely Rachel Sargent. Say hello, Rachel.
Hello.
And Nate Smith is here too, but he probably won't say much. He's working on homework. Hey, Nate.
Hey.
All right, then. We're going to get started on calorimetry, just as we were working before in the last podcast, and then using enthalpy of a reaction indirectly to determine related reactions by applying Hess's law.
Please come to the office.
Oh, and there's my marks on the goofy slide. I always do that. All right, so delta H is called the heat of reaction, but this has a special name. Do you remember what the name of delta H is, Rachel?
Enthalpy?
Right, enthalpy. It's one of our thermodynamic quantities. So enthalpy has this symbol delta H. And if I put a little circle here, then that means at standard conditions. So if you ever see your delta H with a little circle, that just means that it's at 25 degrees Celsius and 1 atmosphere. Sometimes we call this the change in enthalpy because of the delta sign. Really, we're looking at how the heat of the reaction changes as it goes from products to reactants or reactants to products. Does that make sense?
Yes.
All right then. So if we're at constant pressure, then we can use our coffee cup calorimeter, and we can determine the value for Q. So Q is equal to MC times delta T. You've done lots of those before. And at constant pressure, the enthalpy is the same as heat. So that makes it easy to calculate, huh, Rachel?
Yes.
Because we're going to just use MC delta T. Remember, in calorimetry, the substance or the reaction is called your system. So whatever we're focusing on, the system is that substance. And the water that's surrounding your reaction, what would we call that?
The surroundings.
Right. That's the surroundings. So we want to be real clear about exactly what direction the energy is moving. Remember, if the system loses heat to the surroundings, then that is exothermic, right? But if the energy moves from the surroundings to the system, then that's endothermic. Well, what does that mean for an enthalpy change? It means whatever the system loses, the surroundings is going to gain that same amount because of the law of conservation of energy. Whatever is lost by the system is equal to the amount that's gained by the surroundings. But this is really important right here. This sign means it's going in the opposite direction, right? So we got to have the opposite sign. All right then. That allows us to calculate the heat for the system based on the temperature change of the water in your beaker, or the water in your calorimeter is how we usually do it, in your little coffee cup. Seems easy, right?
Yes.
Oh, I erased
Very
all my
much so.
writing first. Here's what we do. We measure the mass of your reactants, and we've got to know the specific heat of your reactants and the temperature change for the reactants. Then we compare that to the mass of your water and the specific heat of the water, 4.184 joules per kmol, and then the temperature change of your water. So those were some things that we practiced in our last podcast, but I wanted to make sure that we all remembered how to do that. Now I can erase my writing, because we've got to go on to a new slide. There's no more room on this one. All right, so then a thermochemical equation is simply describing how much heat is involved in a chemical change. So we have our balanced chemical equation that shows the associated enthalpy change. What's the symbol for enthalpy?
The H.
Right,
Delta H.
delta H. My pen was on pause. Enthalpy change. So as we fill in our blanks during the podcast, then the students who are watching this at home get to fill in their notes. If you don't have your notes packet in front of you, push pause, go get it, then go back and fill in your blanks, guys. All right, so if we have a coffee cup under constant pressure, delta H is the same thing as Q. And if the sign for Q is positive, that means the sign for delta H is positive. And that kind of reaction would be considered endothermic because your system gained energy from the surroundings. And then, of course, we could have the opposite type of change. Suppose the enthalpy is negative. Then what, Rachel?
It's going to be exothermic.
Exothermic, because the system loses energy to the surroundings. There we go. So let's look at an example. I've got a balanced equation here of the reaction of sodium bicarbonate. Hey, that's the same stuff I just used to clean up an acid spill in the back of my room. So sodium bicarbonate will decompose by turning into sodium carbonate, water, and carbon dioxide. This balanced equation is important that first we balance it. And then over here, I've got a delta H value. So in a thermochemical equation, what you'll always see is a piece that shows you what's the balanced equation and another piece that gives you the enthalpy change. And that enthalpy change for that reaction is simply called our heat of reaction. For this particular reaction, this is always the change in heat. And is this one going to require you to put energy in, or is it going to release energy? What do you see?
Release.
It will release energy if it's exothermic, right? And if it's exothermic, then it will have a negative sign.
Endothermic.
Right, this one's endothermic because it doesn't have a negative sign. This is positive 129. And so we're going to have to put energy in to make this one go. Does that make sense?
Yes.
Okay, good. Glad we could talk that through. So let's look at Hess's law. Because some reactions we can't stick a thermometer in to measure the heat change. Like if you were exploding something, I wouldn't want you that close to it, Rachel. So we need to measure it indirectly. We're going to do maybe some related reactions that are close to the reaction we're interested in. Can't think of what I wanted to say. So if we add two or more thermochemical equations to get a final equation, then we can add the balanced equations together, and then we have to add the heats of each reaction. And that would give us the heat of our final reaction. So if we added up two equations, then we could get an overall equation that works for us. I don't think my students have ever seen me do this before. So let's show them the rules, and then we'll show them how to do it, okay? Because Rachel's done this lots of times.
Many times.
Yep. So what are we going to do if we flip a reaction over and write it in reverse? And we have to change the sign to delta H.
Okay.
Oh, yeah. Rachel knew that. She's just afraid to say it and be wrong. Okay, she knows this one, though. If we have to adjust the coefficients by multiplying, then delta H must also be multiplied by the same number. All right, so Rachel's going to run the calculator, and I'm going to write it out so you can see how to solve these. Oh, there the writing. So here's a reaction where we have three related reactions. This is carbon dioxide and water, then forming water from hydrogen and oxygen, and then turning graphite into propane. And then our overall reaction that we want to get is changing CO2 to graphite and oxygen. So it might be hard to see what the overall reaction is and how it relates to these three that we have over here. So let's see, what do we want to have on the reactant side? CO2. Which equation has CO2 in it?
The first one?
Yeah, the first one right here. So we want this first reaction to have CO2 on the left-hand side. And it is. So we don't have to do anything to that number. We're just going to use it the way it is. All right? And we want to end up with graphite on the right-hand side. Do you see a reaction with graphite in it?
3.
Right, reaction 3 has it, but it's backwards.
So you're going to have to flip it.
Yeah, we're going to have to flip it and write it in reverse. And so you could just write the arrow that way, but I want to make sure that I can still see that. I'm going to write it completely backwards. So CH, C3, H8 is all by itself here. And then I had C graphite. How many of those are there?
3.
Okay, I better keep it balanced, huh? And we're combining that with 4 hydrogen gas. Okay, the last thing that we need for this reaction, for our overall reaction, is oxygen. And oxygen in our overall reaction is on the right. So let's find the reaction with oxygen in it. Number 2, it looks like, right?
Yes.
And
2
oxygen's on the wrong side. Oh, and this one too. Good point. Which side do we want the hydrogen on? See, hydrogen's in this reaction, but it's not in our overall equation. So we want that to be canceled out. To cancel it, it has to be on the other side. So if I have 4 of them here, then over here I want to cancel 4. All right. Well, let's leave this reaction as it is. We're not going to flip it, but let's multiply it. Oh, right. Yeah, Rachel just mentioned we changed this reaction around by reversing it, so I have to change the sign by delta H. Good catch, Rachel. All right, so now we're going to multiply this equation by what quantity?
4.
4 would be good. All right, so everything inside here is going to get multiplied by 4, and we'll get 4H2. And what's 4 times 1/2?
2.
Okay, 2 oxygens, and then 4 waters. Okay. I think I want to get rid of this circle because that's messing me up. Yay, I did it. Do we have everything on the right side? Exactly where we want them to be?
And then don't you have to multiply the enthalpy change by 4?
Oh, yep. Rachel's on top of this. We got to multiply the enthalpy change by 4. Sorry, guys. My pen got a little carried away with me. All right, so we're going to multiply this enthalpy change by 4 because we multiplied the reaction by 4. Good plan. All right, now let's see what happens when we add these reactions together. I'm going to go back to black. Okay, so what can we cancel? I've got 4 hydrogens here, and I rewrote it so I could cancel these 4 hydrogens.
Yes. And then you have water.
Okay, water is here, 4 of those, and since I multiplied this by 4, I can cancel 4 waters. All right, I also see propane in this reaction and propane in this reaction. The C3H8, since it's on both sides, we can cancel it out. How many waters can we cancel? I have 2 here and 5 here.
Oh, oxygen.
Yeah, so I can get rid of 2 of these. That leaves me with 3O2 on the top. Okay, and 3 CO2. Let's just add them and see what happens, okay? So all that I have left, here's my reactant side. All I have left over here is 3 CO2. because I've canceled the hydrogen and the water, and I've gotten rid of these oxygens. And the graphite I flipped around, so all I have left is 3 CO2s. We're going to turn that into, on the product side, I have 3 oxygens and 3 graphites. We're getting closer now to our overall reaction, huh?
Yes, we are.
All right. My pen doesn't want to follow my instructions. 3 O2s. 3 O2s. Well, we have 3 times as much as what we want. Any ideas?
We could divide it by 3.
Oh, okay. So if we divide this reaction by 3, then we would have exactly what we want. See that, Nate?
Mm-hmm.
All right. So let's do that. Divide this by 3, and this by 3, and this by 3, and we're left with CO2 makes, that was a 2, makes graphite form of carbon and oxygen gas. Yeah, I'm just going to write graph. And oxygen gas. So since we divided all of this by 2, then whatever our total heat is here, we're going to have to, oh, I divided by 3. Wow. Right? We divided by 3. Then we have to divide our total heat by 3. Okay, so we've got some math to do. We've worked with our equation. Let's do the math part. So we changed the sign of this and multiplied this by 4. Now we're going to add all of these enthalpies together. So I'm going to get my calculator while Rachel works with hers and show you exactly what I want you to do here. So let me get my pen back. Nope, my pointer. So we're going to take 2220, and we're going to add to that 4 times the negative 285. And then we're going to add to that positive 104 instead of negative 104. Is that it?
Yep, and then you divide everything by 3.
Okay, now that I have my answer, we'll divide the whole thing by 3. Good, so this overall final delta H, on my calculator, it says positive 394.6. We better only keep 3 sig figs, it looks like. So let's call that 395 kilojoules. Rachel, does your calculator agree with mine?
It does.
Oh, good. I like it when that happens. Makes me think I might be doing it right. Good. So that's how we do it. And that's really all that I wanted to show you guys in this podcast. But just to make sure you get it, I think we should do a couple more examples. Okay, and these are not in your notes. And your notes say that we're going to continue on and do heats of formation, but I decided to save that for the last podcast so you guys can get more practice with doing these. So what I want you to do now, folks, is switch over to this page in your packet. It says Hess's Law Practice Problems. Rachel and I are going to do some of these with you, and then you'll have less to do at home for your homework. Does that sound like a good deal? I think, Nate, less to do at home?
Yeah, that's a good deal.
All right, that's always a good deal. Okay, so we're going to do number 2, and we'll do number 4, so that you guys can work through the odds on your own. All right, so Rachel and I will do number 2. And I'm going to use a blue pen because this is all printed in black. I want you to see what I'm doing. All right, here's our overall reaction that we want. PCl3 plus Cl2 yields PCl5. So just for extra practice, let's name these. 3 chlorines and 1 phosphorus. How would you name this?
Phosphorus trichloride.
Right, yeah, since they're nonmetals, that's the easy naming. Right, phosphorus trichloride. And then when there's 5 chlorines, how would you name that one?
Phosphorus pentachloride?
Pentachloride.
Pentachloride.
Yeah, pentachloride. So that's what we want to get as a product, pentachloride. Let's find the reaction over here that has pentachloride in it. Is it on the side that we want it to be?
Yes.
It's this guy right here, yeah. Yeah, so that's where we want it to be. How about phosphorus trichloride? This one. Is that where we want it to be?
No, it's not.
Nope, so we're going to have to turn this guy around. And since there's not room up here, I'm going to write it down below. So I get 2 PCl3, pardon me, because I'm doing this top reaction backwards. And that one had 2P plus 3Cl2. Yep. Okay, and since we turned that around, we're going to change the sign of our delta H. So now we have a positive 640. Are we ready to add? I think we have everything where we want it.
I think so.
Okay, let's cancel the things that are the same on both sides. So I have 2 P's here and 2 P's there. Is that it? How about some of our CLs?
We can cancel 3 of them.
Okay, that leaves us then with 2 over here. So I get 2 PCl3 plus 2Cl2 yields 2PCl5. This looks a lot like the last one. Where we're almost to what we want, right? But we have twice as much. What do you want to do with this, Rachel?
Divide it by 2.
Oh, we'll divide this by 2. So that means we're going to take our sum of these reactions and divide by 2. All right, I'm going to get my calculator, and Rachel's going to check my work. I have a circle there. Not anymore. Okay, so now we're going to take a positive 640, and we didn't double that or triple it, just the positive 640, and we're going to add it to the next delta H, which is a negative 886. So that's the sum of the two, and to get the overall reaction, I divide it by 2, so I need to divide my enthalpy by 2. So Rachel, did you get a negative 123?
I did.
Great. And we better put units there, kilojoules. And it looks like 3 sig figs is okay. All right, well, I think that one wasn't too bad.
I don't think so either.
Well, let's look at number 4. Think that might be more challenging?
We'll see.
Yeah, I don't remember this one from last year.
Neither do I.
That was a whole year ago. Let's see what we got. So we want to get CuCl2. That would have to be copper 2 chloride. And we're going to add another copper to it and turn it into copper 1 chloride. Right, because there's 2 forms of copper. And this one has the oxidation state of +2, and this one has the oxidation state of +1. So that's what we're working with. That's our overall reaction. Let's look for these in our equation and see if everything's where we want it to be. All right, we'll start with copper 2 chloride. We want that on the left. And up here I see it. Here it is on the right. So what do we do?
We're going to flip it.
Yep, let's flip it. So I'm going to write it right here. CuCl2. And then on the other side, copper plus chlorine. And we always have chlorine as a diatomic molecule because of Brinkelhoff, right? So since we flipped it, let's change the sign. Call that positive 206. And on this side, do we have everything where we want it to be? Let's see. Looks good to me.
I think so too.
All right, are we ready to add these reactions together?
I think so.
Okay, so let's see. Copper's on both sides, but I have 2 of them here and only 1 of them there. But we multiply this by 2 before we add. What do you think? Because I got to cancel 2 coppers.
Oh, yeah, okay.
Right? So now I'm going to rewrite this again. put my new equation down here. All right, now I have 2 copper 2 chlorides, CuCl2. And on the other side, I have 2 coppers and 2 chlorines. Okay, so now let's add things up. I can get rid of 2 coppers here and 2 coppers there. And then Cl2, I could get rid of one of them, right? Because that cancels one of these. And then the Cu2 CuCls can't cancel CuCl2. They're not the same. So let's see what we get in the end. 2 of these CuCl2s makes...
Why does that make a chlorine instead of a copper?
Because I said I was going to cancel all my coppers, but I didn't. I shouldn't have done that. Now we're going to get a different reaction. Okay. Let's go back and not multiply by 2. Didn't do what we want. So this is like a puzzle. And we work the puzzle to get from what we have to what the question's asking us for. And my way didn't work. We'll do Rachel's way. So this was positive because we flipped it. Now let's add them together. All right. So this copper cancels one of these coppers. And a chlorine and a chlorine goes away. That's what we wanted to do all along. Wow, okay, I made that too hard. So now we're going to add these 2 together, not this one. We got rid of that. So this plus this. Okay, copper 2 chloride over here. And then we add 1 copper to it because we have 1 copper left. We only canceled one of them. And that makes, on the other side, 2 copper 1 chlorides. That worked out a lot better.
Yep, that looks about right.
Okay, good. So since we flipped that, we have a positive 206 plus a negative 136. It's okay. Part of my job is teaching humility to my students. 206. Oh, I can't get to my plus sign. Yep, I did it. Plus negative 136. Okay, I got 70.
Me too.
All right, so then we write delta H for this reaction is equal to 70 kilojoules per mole. All right, so just a warning for you folks when you try this at home or in class. Number 5 has 3 reactions, not just 2 reactions. So it's going to be a little bit trickier, but I have confidence that you can do it. You guys work your way through the puzzles, work together to solve the Hess's law, and if you have questions, of course, you'll bring them to me in class, because we'll be working through some of these in your warm-ups too. Well, thanks for your help, Rachel. I appreciate it.
Oh, no problem.
All right, guys. Have a good evening.